Hi student, in this module, we'll mainly talk about two functions. One is MLE and one is MLE2. From first one from stat4 package and second one for BB-MLE package. Mainly how to use these two functions to get the maximum likelihood estimate of any statistical model or any statistical distribution to get the parameter estimate. And so I'll start with MLE. MLE mainly use the optim function in between to get the maximum likelihood estimate. So how to use the MLE directly from stat4 package, and then we'll learn how to use the MLE2 functions, which is much more robust function than MLE, and where that function would help you to get all other aspect like strong inferential informations and all kind of information criteria, the goodness of fit, etc. All type of things that you will get from this function that you won't get that much from MLE package. And again, the MLE2 and MLE both can be used by defining the log likelihood, negative log likelihood functions. But the MLE2 also allow you to use or make a formula interface. Instead of defining the maximum likelihood, negative maximum log likelihood functions, it would allow you to do a direct formula interface to get the maximum likelihood estimate. So in the second module, we will see how to use the MLE function from stat4 package to get the maximum likelihood estimations. So we'll start with a normal distribution. So first let's generate the normal variable one, say start with seed 1001 and then n equals to 100. So 100 normal, 100 sample size that we can fix it, and that x equals to r norm, n mean equals to 3 and standard deviation 2. Then we formulate the log likelihood function as like LL equals to function mu sigma r equals to d norm x mu sigma minus sum log r. Let us MLE let use MLE command from stats4 package to get the estimates as follows. So first load the library stats4. You may not need to load methods, but sometimes stat4 may not work. I mean MLE may not work without methods, though it should automatically loaded, should be loaded. But if not, you can load the method package, and then you can just MLE LL start equals to list the initial value mu equals to 1 and sigma equals to 1. You will get some warning here that NA is produced, and the results would be given like this. Coefficient is mu is 2.99 and sigma 2.27. Those warnings are a little disconcerting. They are produced when negative values are attempted for standard deviation, and which are two ways to sort out this. The first is to apply constraints on the parameters. The mean does not require a constant, but insists that the standard deviation is positive. For example, say MLE LLL start list mu equals to 1, sigma equals to 1, and method you do the L hyphen BFGS and lower equals to minus infinity to 0 and upper equals to infinity to infinity, and then you won't get the warning, and you will get the estimate as 2.99 and 2.77. These work because MLE calls optim, which has a number of optimization methods. The default method is BFGS, and alternative the LBFGSB method also allows the box constraint. The other solution is to simply ignore the warning. It's neater and producer the same results. For example, the LL equals to say function mu sigma, and then you just write suppress warnings, just pass the d norm x mu sigma within suppress warnings functions that will remove the warning, and then rest of the functions are as it is. Then you can apply MLE start list mu1 and sigma 1, then you will see there is no warning at all, only the estimates are given. So actually you remove the warning. So this suppress warnings function will remove all the warnings that are displaying after running this code. So now we'll apply the linear model here. So let simulate a data as follows. First x generated from R uniform 100, and then y equals to is 2.5 into x plus 3 plus R norm 100 0 0.5 as a sigma. Now to apply the MLE on linear model, define the log likelihood function as follows. Say LL equals to function beta naught beta 1 mu sigma R equals to y minus x into beta 1 minus beta naught, and then you suppress the warnings. For that R suppress d norm R mu sigma and say log equals to 2 because we need the log likelihood, and then return the sum of the negative of the log likelihood value. So sum of R will give you the log likelihood value, and the negative log likelihood value would be returned. And let's get the estimate by the MLE command. So fit MLE LL start list beta naught, the initial value of beta naught is assigned to be 4, beta 1 is 2, beta mu equals to 0 and sigma equals to 1, and then summary fit. The maximum likelihood estimation called MLE, and then the coefficients would be given in this manner. The beta naught, beta 1, mu and sigma, their estimates, their standard error, and also minus 2 log likelihood value would be given here, that is here 1192, 182 that we do for the chi-square and then the next one that we'll see how to apply the MLE2 function from BB MLE package. The BB MLE package designed to simplify maximum likelihood estimation and analysis in R extends and modifies the MLE function and class in the stat4 package that comes with R by default. The major difference between MLE and MLE2 are MLE2 is more robust with additional warnings. For example, the Hessian cannot be computed by finite differences. MLE2 returns a fit with a missing Hessian rather than stopping with an error. MLE2 uses a data argument to allow different data to be passed to the negative log likelihood function. MLE2 has a formula interface like that, for example, GLS in LNME package. For relatively simple model, the formula for maximum likelihood can be written in line rather than defining a negative log likelihood function. The formula interface also simplifies the fitting model with categorical variables. Models fitted using the formula interface also have applicable prediction and simulate methods. The BBMLE defines ANOVA, AIC, AICC, BIC methods for MLE2 objects as well as AIC tab, BIC tab, AICC tab functions for producing the summary tables of the information criteria for a set of models. We will take a beta binomial data, simulated beta binomial data for illustration. First, generate a single beta binomial simulated data set of points as a simple test the fit. Say you have to load the library EMD book and set a seed as 1001, and then x1 is R beta binomial function can be obtained from EMD book package, and then R beta binomial n equals to 1000, probability 0.1, size 50 and theta equals to trend. Then construct a simple negative log likelihood functions, say library BBMLE, then MTMP function probe size theta is minus sum d beta binomial binom x1 probe size theta log equals to true. So this function will give you the negative log likelihood function. Then fit the model, use data to pass the size parameter like this, say m naught equals to MLE2 MTMP. Start, the initial values is start equals to least, probability 0.2 and theta 9, and data equals to least, size equals to 50, and this will give you the results. The probability is 0.103094 and the theta estimate is 10.0758090, and the log likelihood value is minus 2723.5. The summary method for MLE2 objects shows the parameters, approximate standard errors, and a test of parameter difference from 0 based on the standard error and on an assumptions that the likelihood surface is quadratic. Equivalently, that the sampling distribution of the estimated parameter is normal. So if you get the summary of M naught, if you will see that the parameter probe and theta, the estimates are given in the second column. We will get the standard error and the z value and p values showing all are significant, and minus 2 log likelihood would be given here. You can apply confin directly to M naught, but if you are going to work with the likelihood profile, for example, plotting or looking for confidence interval at several different alpha values, then it is more efficient to compute the profile likelihood once. So P naught equals to profile M naught, that will give the profile likelihood, and compare the confidence interval estimates based on inverting a spline fit to the profile based on the quadratic approximation at the maximum likelihood estimate, and based on root finding to find the exact point where profile crosses the critical level. Say if you have the P naught as a profile likelihood, then you can get the 95% confidence interval as confin P naught, and you can also change the method as quadratic approximation, that also give you the 95%, or method uniroot you can change it for say confin M naught method uniroot, that also give you the 95% confidence interval by the method of uniroot. So the three different ways that we have learned how to get the confidence interval. And then plot, we can get the plot of profile, and what we can do, we can plot P naught, then plot dot const str true. So this is the profile likelihood, that confidence interval, the P naught would be plotted, the profile would be plotted, and conf str would be true, and then you will get this plot. The plot method for likelihood profile displays the square root of the deviance difference, twice the difference in negative log likelihood from the best fit. So it will be V-shaped for cases where the quadratic approximation works well. For a better visual estimate of whether the profile is quadratic, use the ABS val equals to false option to the plot method. You can also request confidence intervals calculated using uniroot, which may be more exact when profile is not smooth enough to be modeled accurately by a spline. However, this method is also more sensitive to numeric problems. Instead of defining an explicit function for minus log likelihood, we can also use the formula interface. So the formula interface assumes that the density function given has x as its first argument. If distribution is multivariate, then x should be a matrix of observations and has a log augmented argument that will return the log probability or log probability density if log is true. Some of the extended functionality depends on the existence of S variant function for the distribution that returns the mean median as a function of parameters. Currently defined is S norm, S binorm, S beta, S n beta negative binomial, and S poise. Note that you must specify the data via the data argument when using the formula interface. For example, say M0F is MLE2, then x1 and this symbol, then d beta binomial probability size equals to 50 and theta, then start equals to list, probability equals to 0.2, theta equals to 9 and data equals to data dot frame x1. So these may be slightly more unwieldy than just pulling the data from your workspace when you are doing simple things, but in the long run it makes tasks like prediction and predicting new response much simpler. It's convenient to use the formula interface to try out likelihood estimates on the transform parameters. For example, M0CF equals to MLE2 x, then tilde symbol, and then d beta binom probability is p logis L prob, size equals to 50, theta equals to exp L theta, start list prob L prob equals to 0, L theta equals to 2 and data equals to data dot frame x1. And that the object, if you get the confidence interval confint M0CF method equals to uniroot, so that will give you the 95% confidence interval of the estimate, and confint M0CF method is spline, then that will give the spline method and the 95% confidence interval of the estimates. In the final module of MLE, that is the second module, we learn mainly the use of two functions. One is MLE and another is MLE2 from BBMLE package, and how to extract the different informations from those two our output of those two functions, especially the information criteria, the inferential aspect of the model altogether, that. And we have also seen that MLE2 is much more stronger function than MLE from stat 4, and I think combining both module 1 and MLE module 1 and module 2, I think I tried to cover all the different type of functions and different type of way of applying the maximum likelihood estimate for quite simple model, though it's not much complicated. If a complicated model might need much more sophisticated functions and sophisticated techniques, sometimes hardcore programming might be required, but here by these two modules I'm trying to show you how to actually get the maximum likelihood estimation. It's quite simple type of models and not much more complicated one.